getting to the portion of the design, and I think this will be the second portion of the locus discharges. So we'll take about, I think, 2 weeks, to go over this kind of design aspects. So the first one, we take a look at the effect of adding poles. So we can use an example to demonstrate the concept. For example, we consider this feedback loop system. So the characteristic equations is 1 plus g as h as equal to 0. So the root, we're going to plot again this one. So we can take a look at a simple example here. Say g, the gh, and for example is equal to k as plus a. Okay, so here the a is given, k is the parameters here. We're assuming a is greater than 0, k is greater than 0. So for this case, the root locus of the characteristic equations, and that one basically is s plus a and equal to 0. For this one, we can put it to show it. So for example, here is the real part and the imaginary part here. So here we have two poles here, and s equal to 0 and s equal to minus a. And by applying the rules, the plotting rules, so basically here with the root locus starting from here, from the poles, and also on the real axis, and that should be in the second segment here. And if we continue, basically the root loci, you can see that will be looking like this. Okay. And so that means this one is approximate corresponding to k equal to 0, and this one is k is approaching to infinity. So that is the systems. And we see if we add a pole to the original systems, so we see what happens. So for example, the modified, that means the revised equation becomes like this: 1 plus k and 1 as s plus a and s plus b equal to 0. Okay, so here for example, here we assume the pole is adding up like this, greater than a. Okay, so under that situations, and let me put the two things together. So for this revised system, and let me add it up the two things on the same graph. So for example, the b is here. Okay, so this is the added pole here. So right now, from this one, let me use the different color to draw the root loci for these systems. Okay, so see the blue plot on here. So again, that is a portion. So here, that is, we have a portion here. And right now, we have 3 branches. So this is the third branch. Okay, so this is go to k equal to 0 and approaching to k go to infinity. And for again, for these revised systems, k starting from the 2 pole here. Okay. And from here, you can calculate. You should be able to calculate, for example, asymptotes. The asymptotes you can calculate its orientations. So every asymptote has an orientation 60 degrees, and minus 60 degrees, and 180 degrees. Let me skip up the details. And basically that one you can obtain is by n minus n. Here the n equal to 3, the degree of the denominators, and m equal to 0, the degrees of the numerator here, and this one is equal to 180 degrees plus L times 300 360 degrees, and we keep changing the L. We have these three numbers. The intersections is at the number of the poles and minus the number of the zeros and n minus n. So that one equal to minus a minus b divided by 3. So from here we will be able to estimate the asymptotes, and roughly let me simply draw it a minus b. So that should be something here. Okay, so here I draw it the asymptotes for the new system. So roughly we might be able to kind of be drawing it something like this. Okay. So the inference, here I'm drawing the intersection of the asymptotes arbitrary. Maybe I should have used number. I doubt this intersection should be to the left, to the right of here, right? Okay, but anyhow. So from here, can we, using this example, we can make conclusions is when we add in the pole, basically the adding one pole, that's going to drive the original root loci kind of the push to the right-hand side, push toward the right-hand side. So what that means, system dynamics, corresponding to system dynamics, what that mean? That means the system becomes more agile, which means have a tendency to become less stable or more unstable. Okay, because you can tell using the blue line, the blue has a revised system. It has a chance to go to the marginally stable, and if the K is larger, then it will become unstable. However, and also we, using the blue line, we have the push the system. That means we might have a dynamics that is very close to the imaginary axis. That means have a higher oscillation frequency, but with less damping ratio. So all this evidence saying this revised system by adding one pole is more agile, have a flexibility to become very, I would say, quick dynamics. You good? Okay, so that is the adding poles. Then we can discuss the adding zeros. So again, if you like, let me readdress why the adding poles is the system become more agile. So if you remember, in our traditional dynamic system, so say, let me compare. So if you have the root here, okay, so let me pick number. For example, this root is, say, this is minus 0.1, and this is 10. Okay, so for example, this root corresponding is minus 0.1 plus J10. Okay, so for this one, basically this is the one root compared to if you have a root here. This one, say, is s equal to, say, let me make a 1. Minus 10 plus J10. Okay, so for these systems, for this point, if you have a root corresponding to here, basically you can see the omega n, this one corresponding omega n is about 10. And for these systems, the omega n is about 10 times square cube. So for this one, we can draw the dynamics in the time domain. This one has very small damping ratios. So that one basically oscillating is something like this. Okay. And for these systems corresponding to the time domain, that would be have a little bit faster but decaying quick. Okay. for this system. So that means for here, this one, we can see this system will take a longer time to become stable and to converge to 0. So from here, that is the one way we can look at for any point. For all the system behavior corresponding to the blue line here, that is more agile. Okay, that have a chance to be agile. But for the original system with red one, by all means, it's not agile. That means it will become stable very quickly. Okay, so that is kind of the building on quantitative description. So now we study the effect of adding 0. Adding 0 basically is on the reverse side. So that means you can, before we do this analysis, and you can guess. Okay, so let me pick up the same example, then we see the revised version here. So here we want to, if a 0 is added. Okay, so let me do this one again, and let me do the real part and the imaginary part here. And let me draw the original. So this is original. Okay, original I use the red one, so this is original. Okay. So if we have a 0 added up, so for example here we added up S plus B here. Okay. And here again B is greater than A. So here for this system we have two branches, N equal to 2 and M equal to 1. So basically we have two branches of the root loci. And so from here we can have to do it. So here let me use the blue line. So that is the pole, and 0 is here. Okay, S minus B. Okay, so now for this case again we have two branches, and asymptotes basically is 0 degrees and 180 degrees. And again, for this system, we have two branches. The root loci will occupy the real axis in this portion and also in this portions. Okay, and this one corresponding is the ending of the root loci. So the root loci should converge to a 0, and starting from the poles. So that's starting from the two poles here. And from here you can see the two branches should meet together and split. So there's a breakaway point. And the breakaway point we can calculate is, again, we expect there's a breakaway of this branch somewhere in between. So we can calculate the breakaway. And do the calculation. The calculation basically is we simply do the tk ds equal to 0, and where is k? And dds. So from here we can obtain the expression of k from there. So that one will be equal to minus s plus b as s plus a. Okay. So this is the expression of k we obtain from here. Okay. So then we do this one and equal to 0. So basically, if you solve for this one, then you can get this one as equal to minus b plus minus b squared minus ab, something like this. This one meaning the breakaway point. The breakaway point is we should take away. So the breakaway point is the okay, because here there's a two possible location. One is inside this branch, one is outside. the breakaway point only inside that frame, so we pick out this one. So that one, basically, we can roughly show it, and I just pick up randomly here, okay? So basically, that is one here, and the other one here. So basically, the breakaway at this point, and then going to, so another breaking, so another point should be breaking in. So here we can say they, something like the breaking here, and then the coming to these portions. Okay, so this one is go to infinity. This one approaching to here. So again, the blue line representing is a revised root locus. The root locus for the revised system. The revised system is simply we added up 1, 0 here. So from here, when a 0 is added, you can see that has a tendency to pull the root locus of the original system toward the left side. Any point, anything on the complex plane is more on the left side, that means the system is more stable. The more stable, that means the system is more stubborn to be changed. Its dynamics is more stubborn to be changed. Okay, so from here, this one, we can quickly, using the two examples to make the conclusions here. And I think that's it for these sections.